So this question tells us that 5% of batteries produced by a certain company are defective. On a particular day, batteries produced are inspected until the first defective battery is encountered. Let X denote the inspection number of which the first defective battery occurs. So let's just talk about this question a little bit. So we have some batteries, right? And we're saying that out of those batteries produced at a particular factory or company, we have 5% that are usually defective. If 5% are defective, that means that 95% are not defective. So I got this 95 because we know that things are usually measured in 100%. So if I do 100 take away 5, 95%. Now, it is saying let X denote the inspection number. So just imagine that we have a factory that's making batteries, and every time they make a batch of batteries, they start to do inspections looking for defective batteries. So they're trying to figure out if there are any defective batteries in each batch. So what they're saying here is let X denote the inspection number on which the first defective battery occurs. So they're looking for inspections in a batch, and when they find the first defective battery, that would be considered to be a successful task. So in this question, we are looking for defective batteries. When would we find our first defective battery? Now, this topic in general covers what we call discrete probability. In your syllabus, there are three that we look at. The first one is binomial. We also have geometric probability distributions, and we have what we call Poisson. These are the three probability functions that are taught in discrete probability in applied maths unit 2. Now, binomial deals with selection. It has what we call a cap. So there's a total number of items we can choose from. This is usually represented by n. And we have geometric probability that measures the first success after a certain number of attempts. And the Poisson distribution, what this looks for is the average in a given space or time. Now in this particular question, we're looking until the first defective battery is encountered. This here is my indication that it has to be a geometric because we're looking for the first successful find of a defective battery. It cannot be Poisson because we do not have an average that was given to us. That average is not measured in a given space or time, even though they say that during a particular day. If they told us that in that particular day, an average of 5 defective batteries are found, that is different. That is when we would have considered using this as Poisson. However, in this case, we cannot say it's Poisson. In order for it to be binomial, we would have had to say that we have a batch of 12 and the probability of getting certain number of defective batteries is 5% maybe, and we are trying to figure out how much selections we would have with this combination of defective batteries. So clearly, as you can tell, there's nothing that indicates any of this. Therefore, it's no point in even thinking of a binomial at this point. So geometric is the only logical one here for this particular question. So that is our first defective battery is encountered. A successful find would be determining a defective battery. So that's a good segue into our first question, which is I. It says, state the probability distribution function of X and its parameter. Now, we identify that the probability distribution function in this case is a geometric distribution. And as we said, we knew this because it asks us for the first defective battery being encountered, right? So once we are looking for something that denotes first success, that is when we are considering a geometric distribution. Think of a basketball player. If they are shooting a basketball, you want to know the probability of them hitting their first shot after 5 attempts. That is a geometric distribution that we're talking about because we're looking for their first success. The first success being when they hit their first shot. The parameter for the geometric distribution is usually the probability of that particular success. So in this case, our probability of success is equal to 5%. So we have here 5%, which can also be written as 5 over 100, or as a decimal, it would be 0.05. So I can say that here, probability of success would be 0.05. Remember, what we are considering success here is not having a good battery, but rather finding a defective battery. That is a success in this situation. So usually when we're writing this now as parameters, what we use is X in this case because it said let X denote the inspection number. So you say X is a geometric distribution, and usually it has the value inside here of p. Now in this case, as we say, the probability of success is 0.05, and that is what p represents. So our final answer for this question, we could write it as x geo 0.05. So now part 2 now, it's asking us to determine the probability that the first defective battery occurs at the fifth inspection. So imagine we go in and we did an inspection. Our first inspection, we did not find any defective batteries. Our second inspection, we didn't find any. And we go so forth and so on. And we figure it out on our fifth inspection. So what we are trying to figure out is what is the probability of determining our first defective battery at inspection number 5. Remember, x denotes the inspection number. So the probability when x is equal to 5. Now the formula for the probability of a geometric distribution is written like this. So this small x represents whatever value we're looking at. In this case, we're looking at 5, which is equal to p times q to the power of x minus 1. So in this case, p is our value 0.05. Now q represents the opposite of finding a defective battery. So if here, this P here is 0.05, the Q up here, meaning that we find a battery that is not defective, or a good battery, would be equal to Q in this case, which is 1 take away 0.05. So our value for Q would be 0.95. So putting this into the formula, I will end up with P, which is 0.05 times the value of q. Now we said that q is 0.95, so 0.95 to the power of 5 take away 1. So we have 0.05 times 0.95 to the power of 4. So let's break this down here, right? So I'll start off with the 0.95. What this is saying is that the first time we find batteries that are good, so that's 0.95. And then on the second time we look for batteries again, we found only good batteries, so that's 0.95 again. So this is how we get into the power of 4. So on the third time we have 0.95, which means that we didn't find any defective batteries again. There's a fourth time we didn't find any defective batteries, but then on our final and fifth time we found a defective battery. So on the fifth chance, that is when we found a defective battery. So that is why you see 0.95 to the power of 4 from the formula. There were 4 times that we actually found only good batteries, and there was this one time that we actually found a bad battery, and that was on a fifth chance. So then now when we work this out into the calculator, we'll get our final answer for the probability of x is equal to 5. So when we put this in the calculator, we'll end up with 0.041. 0.041. The next question, it asks us to determine the probability that the first defective battery occurs within the first 3 inspections. Now, we have to think about this for a little while. What does it mean by within the first 3 inspections? That would mean that we have inspection 1, inspection 2, and inspection 3. So we have to figure out what is the probability that it occurs either in the first one, either in the second one, or either in the third one. So we are trying to figure out every probability when it's equal to or less than 3. So in that case, we're talking about we figured out a defective battery in the first one, or we had one in the second one, or we had one in the third one. So these are 3 different scenarios that we consider. Now notice I didn't say P when x is equal to 0. Why? Because the only way I can find a defective battery is if I actually make one inspection. I have to at least make an inspection, which is one inspection, to find a defective battery. If you were to think of it as taking a shot, if I was saying that we're looking for my first successful basketball shot, obviously in order to occur I need to take a shot. So if I took 0 attempts, there's no way I'm gonna find whether or not that would have been a successful attempt. Therefore, that's why I don't have here x is equal to 0. So I have to figure out for x is equal to 1, x is equal to 2, x is equal to 3, and because these are the 3 different options or possibilities, I have to add them together in order to finalize this answer. So then using the same formula that we used before, we would say p q to the power of x minus 1. So in this case, we would have p, which is 0.05 times 0.95 to the power of 1 minus 1, and that's going to be equal to 0.05 times 0.95 to the power of 0. So that's going to leave us with 0.05. So now for the next one, we didn't find one in inspection 1, but inspection 2 we found a defect. For that one, we're using the same formula, but this time we're going to say 0.05, which is P, multiplied by 0.95 power of 2 minus 1. So that will leave us with 0.05 times 0.95 to the power of 1. And this would simplify to 0.048. Usually try to put them to 3 decimal places. So the last one that we have to do now is on the third inspection. So we're going to have 0.05 times 0.95 to the power of 3 take away 1. So we'll end up with 0.05 times 0.95 to the power of 2. So this is going to be equal now to 0.045. Now to get our final answer for this question, we need to add up all these possibilities to get our final answer. So we'll get 0.143. So for question number 4, it's asking us to determine the expected value of x. So there is a thing that we call the expectance, and each distribution has an expectance, usually written as E x, and the formula for this one is simply 1 over p. For the geometric one, it's 1 over p. Remember, there's one for Poisson, is also a separate one for binomial as well. Remember, this expectance here is 1 over p specific for geometric. So we know what our value of p is, so that means our expectance would be equal to 1 over 0.05. So based on that, our expected value is 20. So we expect that if we was to do a particular run of inspections, we would really truly expect to find a defective product by 20th inspection. So assuming that the first 12 trials are free of defect. Now when you look at this is giving us a condition. This here is a condition. So we know that this is conditional probability. Now the second piece says compute the probability that the first defective battery will occur at the 20th inspection. So let's talk about this one here first. We have two different scenarios here. We have event A. So event A, what this is saying is that assuming that the first 12 trials are free of defects. That's the first event. Now event B is an event where we have first defect on 20th inspection. For event B, what we would have here is that in this particular scenario, we are looking for the probability when x here is equal to 20. So earlier we did for when x was equal to 1, 2, and 3, but in this time we're looking for when it's equal to 20. So let's work this out and then we'll talk about all of this together because this question has a lot to unpack. So what we're saying here is that the probability for this one would be equal to p q to the power of x minus 1, the same formula. So in this case, it's going to be 0.05 times 0.95 to the power of 20 take away 1. So therefore, we'll say that 0.05 times 0.95 goes to the power of 19. This here will give us 0.019. That's just the probability of event B. So we'll talk about event A and event B a little bit now. We said that we have event B, which is the probability when we have our first defect on the 20th inspection. Now remember I said earlier that this is a conditional probability situation because they're saying that assuming that the first 12 trials are free of defects. So this is something that already occurred. So we are establishing that before we found the first defect on the 20th inspection or any scenario that would allow us to find it on the 20th inspection, we had to have had 12 free defects. 12 trials, 12 inspections, and all 12 of those were free of defects. So that is what event A is. So remember from earlier we said that this formula allows us to denote, say for instance, every time I get a non-defective situation, it would be 0.95. If I get a next non-defective situation, again, it would be 0.95. And then when I do get a defective one, which would be considered successful, I would have 0.019. 0.05. Let's get a little understanding of a formula to basically help us to figure out how we would calculate the probability for event A. So we are saying that the formula for geometric distribution is written as this: pq to the power of x minus 1. So what this always does, it figures out the one success that we have. Say I did 3 inspections. My first attempt would be no defect. Second one, no defect. On my third one, I'm finding a defect. That's why we would have the formula like this. So if this was x, meaning our third attempt, we would say this is pq to the power of 3, take away 1, which is pq to the power of 2. So what we're saying is we're going to have two q's, which is this one here and this one here, representing the times that there was no defect found. This third one would represent when a defect was actually found. Now, let's link this back to 12 defects free. So we do not find a defect. Technically, if we do not find a defect, that means our first attempt, 0.95, there was no defect. The second time we do it, no defect. Third time we do it, no defect. And we keep going on and on and on till we reach our 12th inspection. And on that time, we still do not find any defects. Therefore, what we're saying is that we're only gonna potentially find defects on the 13th one, the 14th one, 15th one, 16th one, 17th one, 18th one, 19th one, 20th one, and so forth. So that means we would say 0.95 to the power of 12. Because after 12 attempts, we still would not find any defect. So that's why we're saying 0.95 to the power of 12. This would give us 0.54. The alternate way of working this out is basically saying that we want 12 trials to be defect free. What we are saying that we are okay with having our first failure on the 13th try, then from there onwards 14 try, and so forth. So in this case, our probability would be when x is more than 12, because we do not want to have a defect that is under 12. It must start after the number 12, so it has to be more than 12. Now if we try to calculate this, we'll be here all day because we can go straight up to infinity. However, the alternate to doing this is figuring out what it is for when it's equal to or less than 12 and then subtracting that for 1. So another way of writing this or solving this would be saying 1 minus probability of x being less than or equal to 12. That's the other way of trying to work out the probability of having 12 trials defect free, and then we could figure it out by having the defects from 12 down and then subtracting it from 1 to get the overall answer. Now imagine trying to do this in an exam. We would have to start from 1, 2, 3, 4. We already did 5, 1, 2, and 3. We would have to do 4, 6, 7, 8, 9, 10, 11, 12. That is too time consuming, and it would still give us the same answer as if we were to do it with 12 successful situations. I did a cumulative distribution function for the geometric so you can see what the value would be for p x is less than or equal to 12 if we wanted to work it out one by one straight up till 12. As you can see here, this is a cumulative distribution. So we want to look for the value when x is 12. So when x is 12, this is the number that we expect to see, 0.4596. So that is a sum of all the probabilities come straight up, which gives us 0.4596. So as you can see here, for instance, we have the cumulative from when x is 1 is 0.05. Then we add it for when it's 2, and we keep adding and adding and adding until we reach 10. And as you can see here, when we reach up to 12, it's going to be 0.4596. At 12, we expect the probabilities that we would have done for each to add up to 0.4596. So then, if we write that to 3 decimal places, we would have 0.46, because 0.4596 would go to 0.46. And then if we use this formula here, what we would end up with is 1 take away 0.46, which would give us 0.54. So could either do this the long way in the exam or do this, it's just for 4 marks. This is the best way to do that. So now we have the probability for event A and the probability for event B. So remember we said that this is a conditional probability. So what we're saying is that in this case, we're looking for the probability of event B given that event A already occurred. Event A meaning 12 trials defect free. So the formula for this is written as A intersection B over the probability of A. So we already have the probability of A. Now we need to talk about the A intersection B now. In this situation, 0.019 would solve as this here. Why? It's already an intersection for what it is. Why is that the case? Because we're saying that the first defect on the 20th inspection or first defect occurs on the 20th inspection. This event B is a subset of event A. So if we had a pool of event A, inside of this we would have event B, which would represent the first defect on 20th inspection. Remember, there were no defects up until 19. Similar to this one here, this one says there's no defects up till 12. So we already covered the fact that there are no defects in event B up until the 20th time. So this probability will be covered inside of this defect. The first trial, no defect. Straight up to the 12th, straight up to the 19, no defect. The first defect was in the 20th. So therefore we know that this 12 trials defect free occurs already with B. So we already know that B is one that can fit inside of A because there will be no defects past the 12 trials. Therefore, B is a smaller member of event A. Remember, event A would include a defect on the 13th, 14th, the 15th, straight up all the way up to infinity, and event B just happens to be one of those ones. So therefore, we know that the intersection is already what we have as this value here. So when we are answering this now, we would have to say 0.019 over the probability of event A, which is 0.54. So our value for that would be 0.019 divided by 0.54, which would give us 0.035. And that's our answer.